Hi, welcome to part 2 of the chapter 12 video on probability. So, we talked about probability models last time and looked at examples with dice. So we're just going to do a couple more terms first of all. Our first term is going to be finite. Finite means limited in number. Another way to think of this is not infinite. Most of us have a vague idea of what infinite means. So examples of finite lists of numbers would be 1 through 5. 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5, 6, all the way up to 100. But they don't have to be listed every number starting at 1. It could be 2, 4, 6, 8, 10, all the way up to 100,000. It doesn't even have to have a pattern. It could be 1, 5, 2, 13, 8. But a finite list means there's an end. It doesn't go on forever. Going on forever is infinite. Now, another word, discrete, means listable. Another way to think about that is you can write your list in such a way that you can tell where in the list a number will be. An example of this would be what we call the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, going on forever. They go on forever, but it's listable because I know exactly where the number 372 would be. It'd be right after 371, right before 373. And as 1 is the first number and 2 is the second number, it's going to be the 372nd number on my list. Just to give another example, I could say 2, 4, 6, 8, ... all the even numbers. Then the number 20 would be the 10th number on my list, right after 18 and right before 22. So if you can write a list in a way that it might go on forever, but you can still know exactly where things are, that is called discrete. Things that are not listable would be all the real numbers between 0 and 1. There are infinitely many numbers, but not only that, let's think about it in decimal form. Where would 0.413227 be? What might think of the most obvious way to number something would be to start with 0 and move our way up. But what's the number right after 0? 0.1? Well, what about 0.0001 or 0.000001? There's no way to list this in a reasonable manner because there's just too many numbers. We're not going to go into this class, but there are small infinities and there are big infinities. And listable infinities are small, and this infinity here is large. So, all finite lists that stop, are discrete. And so we're going to kind of use those two interchangeably in this class. And things that are not discrete, we're going to work with things called continuous. Continuous lists contain all values in a given range from, say, A to B. And we can count A to B, that's what the square brackets mean, we include those numbers. Or we can throw them out, every number between 0 and 1, but not 0 and 1 themselves. These are infinite, and they're in this group, and they are uncountable, unlistable, so they are not discrete. So, everything in this class is going to be listed either under discrete/finite or continuous. So, the random phenomena is just the plural of phenomenon. The random phenomena we see in this class will be either finite and therefore discrete or continuous. For finite things, we're going to use probability models generally in table form. They don't have to be, but it's the easiest way, like we did in the previous video with dice. For continuous lists, we must use a density curve. We can't make a table of infinitely many things, and so we're going to use the graph of a density curve like we've done already in the past. So some examples of continuous distributions that we've already seen are uniform distributions and normal distributions. So we're going to take all that stuff we did before and just change it up slightly to be looking at probabilities. Instead of asking what percent of the normal distribution is in this group, I'm going to say, you pick someone at random, what's the probability it's in this group? So proportions and percents become probabilities. But as we saw before, since the probability is defined as a proportion, these are literally the exact same question, just given different perspective. So, an example. Let X be the height of American adult women. Suppose X, squiggly line, that's called a tilde, n parentheses 64.2 inches, comma 2.8 inches parentheses. What that means, this little single squiggly, if we do two squigglies, that means approximately equal. When we do just one, it means has this distribution. So this is saying X has a normal distribution with mean 64.2 and standard deviation 2.8. It's just easier to write that way. So adult women have a normal distribution, height of American adult women have a normal distribution with mean 64.2 and standard deviation 2.8 inches. We choose one woman at random. What is the probability that the woman is between 5 feet and 5 feet 3 inches tall? Well, the first thing we have to do is notice that our data is given to us, our information is given to us in inches. So we want to convert 5 feet into inches. So we multiply by 12. I happen to know that 5 feet is 60 inches. And 5 feet 3 inches, well, 5 feet is 60, 3 more would give us 63 inches. So what we're asking is what's the probability that our person is between 60 and 63 inches, or the probability that X is between 60 and 63 inches. Okay. Oh, I have to change this slightly. Oh. No, never mind. So, what do? Well, since it's normal, I'm going to start with a picture. Normal, my mean is 64.2. I don't care to draw my standard deviation, and I'm looking for between 60 and 63. And again, it doesn't matter exactly where I put the numbers as long as they're in the right order. 63 is less than 64, and 60 is less than 63. So this is the area I want. And again, we can do this either with our calculator or by hand, and I want you to be able to do both. I'll do A with my calculator, I'll do B by hand. With our calculator, we'd use normal CDF. Our left boundary or our lower boundary is 60. Our upper boundary is 63. Our mean is 64.2. And our standard deviation is 2.8. I get out my calculator. And I get 60 to 63, 64.2, 2.8. I get 0.2673. Now, as this is a probability, that is a perfectly good answer. If you prefer, you can write it as a percent. Doesn't matter to me. So, there's a 27% chance, roughly, that a random woman we pick will be between 5 foot and 5'3". Okay, now I changed it up a little. Instead of giving it to you in words, I give it to you in notation. Find P parentheses X less than 60 or X greater than 72. So in other words, this is saying find the probability of getting a person shorter than 60 inches or taller than 72 inches. And it's good to be able to read notation and be able to use words. And so again, I'm going to start with the picture. 64.2 is our mean. Here's 60, here's 72. All that matters is they're on the correct side. I want less than 60. I want greater than 72. What we need to notice is that there's no overlap. There's nothing that's going to be in the 60 group and in the 72 group, and that means that we can turn this into the probability that x is less than 60 plus the probability that x is greater than 72. I believe that was rule number 3. Or's turn to plus if there's no overlap. So if I'm going to do this using my table, then the first thing I need to do is I need to standardize, because my table only uses standard normal. And so I'm going to standardize over here. Remember, our formula is the x value we care about, 60, minus the mean divided by the standard deviation. 60 minus 64.2 divided by 2.8 is negative 1.5, and I'm going to round it to negative 1.50 because our calculator needs 2 places after the decimal. So that is what our 60 becomes. Our mu becomes 0 because it's standard normal, know that. And our 72, we standardize. Now when putting this into your calculator, if you're going to put this all in one big step, make sure you put parentheses around the top, because otherwise your calculus say, oh, I know order of operations, division comes before subtraction. Or you can do the subtraction, hit enter, and then do the division. Okay. Now this one didn't turn out quite so easy. I'm going to round it to 2.79. Now the answer was 2.785714, but I rounded it to 2.79 because after the 8, let's write this down. Oops. 2.7857 ... I want to round it here. Since this number is 5 or bigger, it pushes the 8 to a 9. So it's 2.79. Okay, so now I'm going to look up both of these numbers on my table. But actually, I'll show you a trick. When I look up negative 1.50, I get 0.0668. And that tells me that this area is 0.0668. Now, if I look up 2.79, that's going to give me this area, the area to the left. And I don't want the area to the left, I want the area to the right. So I could look up that number and then subtract from 1, and there's nothing wrong with that. But I'm lazy. And I remember that the right tail and the matching tail on the other side are equal because this is symmetric. So instead of looking up positive 2.79 and then having to subtract for 1, I'm going to look up negative 2.79. Negative 2.79 is 0.0026. And that gave me what would be the little left tail, which is equal to my little right tail on the other side. And so that's just a nice way to avoid having to subtract from 1, is to look up the opposite sign once you've hit a z. So our probability for the 60 is 0.0668. Our probability for the 72 is 0.0026. We add those together and we get 8 plus 6 is 14, carry the 1, 8, 9, 6, 0. So the probability our person is either shorter than 5 feet or taller than 6 feet or shorter than 60 inches, taller than 72 inches is about 7%, 0.0694. So, in essence, these are the same kind of problems we've seen before. We just changed the context to, I'm picking one person at random, what's the probability that they are this thing, as opposed to what percent of people are this thing. So real quick, some definitions. A random variable is a variable whose value is a numerical outcome of a random phenomenon. We kind of used that here. It was slightly bad wording. What I probably should have written was x is the height of a randomly chosen American adult woman. Now, the distribution is the same for either. The distribution of the population causes the probability distribution, because the probability is literally the proportion from the population. But technically X is defined to be the answer you got from the random thing. So we want to throw in the randomness into our definition if we're going to use it as a random variable. The probability distribution of a random variable gives the possible outcomes and the probability of each outcome. So it is literally the same thing as a probability model. We just give it a new name, the probability distribution of a random variable. So no big deal, it's all the same thing. And a last little definition, a personal probability is a probability whose value differs for each person. And let me give you just a quick example. What's the probability that you pass this class? I'm guessing that instinctively you made up a number just now. And you probably made up a different number than the other people who are going to watch this video. Some of you probably said 0. Some of you said 50%. And none of you are wrong necessarily. I don't necessarily think you're all right because you might not believe in yourselves. But just because you picked a different answer than someone else doesn't mean one of you is wrong. You have different probabilities. I might ask you, what's the probability you go to the grocery store this weekend? Some of you are going to say, 100%, I'm totally out of food. And some of you are going to be like, 50%, 25%. Some of you are like 0%. It's almost the end of the month and I have no money. Again, you're going to have different answers, and there's no right or wrong answer. So that's what a personal probability is. It's a probability whose number is dependent on you, what you think at that moment. So that is the end of chapter 12. It's all about probabilities. So if you have any questions, please come and see me. Have a good day.